Okay, good afternoon, everybody. Thank you very much to our esteemed session chairs. This is a talk that was planned to be delivered by my postdoc, Dr. Arslan Akbar. But the title is Concrete Mix Design Optimization using a combination of machine learning and Bayesian optimization for developing low CO2 and low cost or cost efficient mixtures with SCM. Let me see if this would work. Yeah. All right. So just as a brief motivation, we all know that concrete is a great material, but at the same time it has a carbon problem. And there are lots of conversations that have been going on for years as to whether concrete should be replaced with another material or how improvements in concrete could be made. Not to dwell too much on that, but essentially at the scale that we use concrete for many different types of construction, from infrastructures to homes and so on, other alternatives are not scalable. So here's an example that Arslan has identified as to if we were to replace concrete with timber, we would need a forest 1.5 times the size of India from the reference that is cited there. So the merit or the conclusion is that concrete is with us, is here to stay, and we have to continue to make improvements in concrete to make sure that not only it delivers the performance, but also it has an acceptable and much improved environmental impact, including carbon footprint. Many of you are familiar with this PCA roadmap to carbon neutrality, which essentially talks about various strategies that could be used to decarbonize concrete. This could include more efficient clinker production in cement kilns that are energy efficient and maybe powered by renewable electricity, use of less clinker in cement, for example, high SCM mixtures or non-Portland cement mixtures, and this talk essentially dovetails on that point for the most part. Improving concrete, such as lean mixtures, avoiding over-design, use of recycled aggregates, use of seawater, and so on. Improving construction and maintenance, and last but not least, carbon capture and mineralization. Okay. Over the years or over the decades, as we are asking for more and more from concrete to deliver high performance at low environmental impact and also low cost, concrete mixtures have become more and more complex, such as mixtures that are low clinker, high SCM, maybe using recycled aggregates or other recycled materials. And as such, the conventional, essentially trial and error based of concrete mix proportioning is too slow and too inefficient to deliver optimum results in a timely fashion. So we need to have new tools, and AI is a very timely tool to allow us to arrive at these optimum mixes. Okay. So the solution that is offered in this talk is, and I'm sure in this session or this dual session for the most part, is using AI to improve and accelerate design of concrete materials. Okay. Mixed proportioning and others. The strategy that is specifically talked about in this slide is a combination of machine learning and Bayesian optimization. And if I can maybe talk a little bit more about this. So this, in this presentation, I'm going to talk about two models that kind of work hand in hand. One of them is this machine learning model, which bridges between, maybe, let's see if I can use that. Well, that's not going to show here. Okay. So the machine learning model, which is the top one, bridges the process to performance. So essentially, it uses input parameters such as ingredients of concrete, like what are the properties of cements that you're using, what are the properties of SCMs that you're using, aggregates and so on, and also mixed proportions, such as water-cement ratio, SCM to cement ratio, the aggregate content, and so on. And it links these input parameters with performance of concrete. And performance could be workability, could be mechanical properties, could be durability, and so on. And there has been a lot of very good work on that topic over the last maybe 5 to 10 years. The second model, which is this mixture optimization model, is in some respect an inverse of the first model. So the second model still uses the ingredients that are available to, let's say, a practitioner, let's say a concrete, ready-mix producer. The composition of cement that they have, the types of SCMs that they have, the type of aggregates they have, as well as the performance that is needed, like what strength are you designing for, or what workability you're designing for, and then it runs an optimization in conjunction with the machine learning model to identify what are the best mix designs that delivers the performance but minimizes the CO2 or minimizes cost, or another factor or property that you may ask the model to do, to minimize or maximize. Okay. So in this work there are three objectives that were pursued, or three main tasks that was looked at and pursued. One was developing a database that links concrete mix designs with performance. And in this particular case, the performance was compressive strength. I'm sure everybody agrees that a prerequisite of any good machine learning model is a good database. Okay, so the database that was kind of put together here included about 450 data points, which may not look a lot of data, but there are some unique features with this data. One is that all of these are binary cement-SCM mixtures. The second feature is that for all of these mixtures, the pozzolanic reactivity of the SCM has been tested using this relatively new ASTM test, which is so-called R3 test, ASTM 1897, that allows us to quantify the reactivity of any given SCM. So in this database and the machine learning that is built on top of this database, not all fly ashes are considered the same. Not all calcine clays are considered the same. The amount of reactivity, or how they contribute, how each individual SCM contribute to strength, is considered and is built into this model. At the bottom, if you could read, there is an example of how the data looks like in this database. So we have the properties of cement with properties of SCM, the mixed proportions, and the compressive strength. Okay. So I mentioned about this test, ASTM 1897, and that was the biggest limiting factor. I mean, why we were limited to 450 data points was that we could amass 450 rows of data based on in-house data, industry contacts, and literature data, for which we had a binary mixture, a concrete mixture with one cement and one SCM, and the pozzolanic reactivity of the SCM was measured. For those of you who may be less familiar, this is a test that is essentially, it makes a mixture of SCM and lime, or hydrated lime. So we have the SCM, 10 grams, 30 grams hydrated lime, about 5 gram calcite, mix it with an alkaline solution with a known composition or a specified composition, mixes for 2 minutes, and then seal cured at 40 degrees C, and measures the bound water or cumulative heat of reaction at 7 days using isothermal calorimetry or a furnace. Okay. And the graph that we see on the left is essentially showing different ways of measuring pozzolanic reactivity. This is data by Lee et al. This is from Europe on how different ways of measuring pozzolanic reactivity correlates with compressive strength of concrete. And we can see that this R3 test not only has low variability, but also very high correlation with compressive strength. So that's why we decided to use that as part of this strength prediction machine learning model. Okay. Right. So the other two research objectives were, so the first objective was to develop a database. The second objective is to build a strength model. And this is a machine learning model based on Gaussian process that predicts compressive strength from concrete ingredients and mix design. So it takes the properties of ingredients, it also uses your mixed proportions, and it predicts the compressive strength of the resulting concrete. And I'll talk about the predictability, the R-square, root mean square of error, and all that in the coming slides. The third piece of this work is this Bayesian optimization model, which essentially says that if you tell the model what type of cement or what properties of cement, like oxide composition, fineness, and so on, and what type of SCM and what reactivity of SCM you have, this Bayesian optimization can offer you an optimum mix design with minimum CO2 and minimum cost while meeting a specified target strength. Okay. So before we get into the actual machine learning model, these are some density plots that show how, based on the 450 data points, how different parameters, such as the lime content of cement, such as pozzolanic reactivity of SCM, water-cement ratio, and so on, impacts the compressive strength of the data that is available in the database. Okay. Now let me talk a little bit about the building of the machine learning model, whose objective is predicting strength. So it is a random forest-based model, which is using Bayesian optimization for hyperparameter tuning with a tenfold cross-validation. So those of you who work in this space are familiar with this terminology. One of the things that I want to highlight is this issue of feature importance and sequential model building and evaluation. So the model actually had 16 input parameters that are listed down here. Initially had 16 parameters, such as water-cement ratio, SCM to cement ratio, reactivity of SCM, aggregate content, so on and so forth, and used all of these 16 input data to predict the compressive strength. And as part of building the model, there is a feature importance chart or feature importance process that was made, which shows what's the significance of each of these parameters. So water-cement ratio was determined to be the most important, not surprisingly. The SCM content was very important. The reactivity of SCM was very important, and so on. So these are ranked in that order. And then in order to reduce the dimensionality of the model, what Arslan did is that he started essentially knocking off sequentially the parameter that had the least significance, so the 16th parameter, and saw how that impacts the predictability or prediction ability of the model. And then knocking off the 15th parameter, 14th parameter, and so on. And here you can see the R-square, or essentially the prediction capability of the model. You can see that it remains constant practically up to about 5 input parameters. And the last 5 input, if you start removing them, you see that the prediction capability drops significantly. So eventually, the final model was based on those 5 parameters. And let me say, so water cement, SCM content, reactivity of SCM, aggregate content, and the calcium oxide content of the cement. Okay, so this is a little bit more kind of under the hood, the nuts and bolts of the machine learning model to predict strength using this tenfold cross-validation. Some of these, completely honestly, I am not, super, I would say expert or familiar with. One thing that I know is that out of these 450 data points, 20% of the data was separated randomly and was never used in the training of the model. And the remaining 80% underwent this tenfold cross-validation and essentially splitting into 80-20 of training and testing and so on. Okay. The final model that he arrived at had these prediction capability of mean square error of about 4.4 megapascal, root mean square error of 5.68, and R square of 0.88. Okay. Now let me talk about the Bayesian optimization model. So now we've built a model that can use the mixed design and properties of ingredients to predict strength. Now we want to turn this on its head, and we want to say these are the ingredients that we have. We want to arrive at, let's say, a 35 MPa strength or 45 MPa strength, whatever strength that you want to specify, and then you're asking the model to give you a mixed design based on the ingredients that is at your disposal that results in the minimum CO2 and minimum cost. So the inputs are the ingredients that are available and the target performance, the target strength that you're specifying. These are the 5 parameters that machine learning model identified as most significant in predicting strength. And there are so the bottom 2 are input into the Bayesian optimization model. We know what kind of cement we have, we know what kind of SCM we have, and what reactivity it has. The Bayesian optimization would tell us the first 3 parameters. For that, we will specify a range. We say water-cement ratio has to be between 0.24 and 0.5. You can change the range as you want, but we want to make sure that the model kind of stays within a reasonable range of these variables. We also provide the model with the unit cost and unit CO2 of the ingredients. One of the inherent things about this Bayesian optimization, well, the machine learning Bayesian optimization is this concept of convex Hall envelope, which means that we have to be very careful to make sure we never ask the machine learning model to extrapolate. Okay, so we know, what is the range of different parameters that the model was trained on, but if we only say, well, as long as we stay within these ranges, we're fine, that's not correct, because you may have, for example, data points in your database that had a 0.24 water-cement ratio, but the SCM to cement was never, let's say, at 0.6. So if you're asking a model to predict something like that, you are inherently asking the model to extrapolate. So this is very important. And this is the graphical illustration of that. So it's an n-dimensional convex envelope that it's like produces a cloud of all the data that was used to build the model. And we need to make sure that any mixed design that is resulting from this modeling falls within this cloud and doesn't fall outside of it. Okay. Other than that, it's an optimization. The Bayesian optimization picks a value randomly between these 3, makes sure that it's within the envelope, uses the machine learning to predict the strength. If the strength doesn't meet the target, let's say 45 MPa is what we ask, 45 MPa with a tolerance. We have to specify a range as opposed to an exact value. If it doesn't meet the strength, it goes back to this feedback loop. It says no, it imposes a penalty, and it keeps going. If it does meet the strength, it identifies the mixed design, or it finalizes the mixed design. It calculates the cost and CO2 associated with that, and it registers that as a viable mix. And then it goes through this loop, and then it identifies if, which mixture has the least cost and least CO2. And if there is, if these 2 are conflicting, you have to just write down a utility function to resolve that conflict. Okay. So very quickly, I'm going to show you 2 examples. This is a mixed design that was based on a cement fly ash. The model was asked to produce a 45 a plus minus 5 MPa mix with minimum cost and minimum CO2. And the model started at a data point within the ranges that we told the model that you can operate in. And through the optimization arrived at about 250 iteration arrived at a final mix design. And the final mix design was 33% less CO2 than the initial one and 12% less cost. And what's important is that if we compare these with industry benchmarks, and one of the good industry benchmarks is NRMCA data that says, for a mix with 45 MPa, what is the typical CO2 footprint? And if we compare, this model is, nearly cutting the CO2 in half compared with that benchmark. This is another example, same concrete except that this one is with calcined clay as opposed to fly ash. Okay? Again, it starts from here, 250 iteration arrives at the optimum cost and CO2. And of course, optimum means that the difference between previous iteration does not exceed a certain threshold. And it can cut the CO2 by 22% versus the initial starting point and by 37% compared to NRMCA baseline of the same strength. So let me kind of summarize some of the things that I was able to show today. One is that this work essentially delivered on 3 fronts: creating a database of concrete mix designs that are cement-SCM combinations with pozzolanic reactivity of SCM known. It developed a machine learning model to predict strength, and it developed a kind of a complementary Bayesian optimization to optimize the mix design to deliver a given strength. The strength model is able to predict a 20-day compressive strength with a mean absolute error of about 4.4 MPa. And then the mix design models offer an optimum mix design with minimum CO2 and cost while meeting a target strength value. I think also it's equally important to show that this is just an example of what can be done. It's not an endpoint. It is showing a framework of how we can use AI in mixed design models. So of course, if you expand the database, you can improve potentially the prediction capability. And also, more importantly, if you expand the database into things like ternary mixtures, into other properties of concrete beyond strength, there is a lot of utility that can be essentially extracted out of models like that. Okay? So with that, thank you very much for your time, and I'll be happy to answer any questions to the extent I can.